All right, good afternoon. Just picking up where we have left off with complex numbers. Again, you have as your centerpieces. Again, we have the letter I, okay, which we have equal to the square root of -1, and from which, if we were to square both sides, okay, we also have that I squared is equal to -1. And once again, we have the standard form of a complex number is going to be a plus bi. And just some things to mention, okay. Some things about the operations between complex numbers. Now, among the earlier examples, okay, we looked at reducing a single radical that contained a negative, where we have like the square root of -25. And I just want to mention, okay, now when you're working with complex numbers, okay, when you're operating with complex radicals, okay, like the square root of -36, for instance. Now I'll place emphasis on this, okay, first express the radicals in terms of the letter I. Okay, I'll give you some instances here. Okay, if you have like working with, say, radicals, okay, and you have, let's say if you have the operation of addition, okay, with terms that once you convert in terms of I, you'll be able to combine. Okay, now let's say we have something like the square root of -9, and we have plus the square root of -4. Okay, so for the square root of -9 plus the square root of -4, now -9, okay, that is going to be where the square root will be at 3i. Now for -4, okay, the square root is going to be 2i. And so we have here that 3i plus 2i is equal to 5i. And let's say that if you were to go with, say, just taking the difference between complex terms, and we'll say that we have, let's say here, we'll go with the square root of -48, and say we'll have minus, okay, and we'll say that we have minus the square root of -12. Okay, now we don't have perfect square numbers, or the opposite sign of perfect squares, inside the radicals, but we will be able to reduce. Okay, so right now for the square root of -48, we have the square root of 48i minus, and for the square root of -12, we have the square root of 12i. And again, 48 and 12 are not perfect square values, but we can reduce these. And for what we have with the square root of 48, okay, now the highest perfect square that is divisible into 48, okay, you got among your perfect squares, you have 4, 1, 4, and then you have 16, and 16 will go into 48 3 times. Now 12, not a perfect square value, but it is the multiple of a perfect square that is greater than 1, where we have at 3. So for what we have here, for the square root of 48i, we have what's going to be the square root of 16 times, the square root of 3i. And for the square root of 12i, you have square root of 4 times the square root of 3 times I. And reducing. So you have for the square root of 48i, you have 4 times the square root of 3 times I. For the square root of 12i, you have 2 times the square root of 3 times I. Now we have like terms to combine. Okay, so you have like, not only because they're in the variable I, but also we have the square root of 3. So you have 4 of square root of 3i minus 2 of the square root of 3i, and that difference comes out to 2 times the square root of 3 times I. And if you put the variable in front of the radical, okay, this is our other possible display. All right. And let's say that, okay, so for what we have with addition and subtraction, okay, the process is fairly straightforward. It is with items and the other operations that you had to be careful. Now we say if you have like, let's say we have the square root of, let's say we have the square, so we start out with square root of -9 and the square root of -4 adding together. And we'll do likewise with multiplication. Okay, so you have the process. Okay, so when you're operating with complex radicals, first express the radicals in terms of I. Okay. Okay, so you have the square root of 9i. You have times the square root of 4i. And you could go ahead, have gone ahead and written this as 3i. So we have the square root of -9, so we have 3i. Square root of 4i, have 2i. Now 3 times 2 is 6. And guess what? The product would have to be 6i squared. Now, let me mention something. The reason I'm saying to go ahead and extract the I for each is that one can make the careless mistake of taking the square root of -9 times -4, which would be 36, and to say the square root of 36 is equal to 6. But since we're dealing with the complex number system, you're going to write the radicals in terms of the letter I. So once you multiply together, we have I squared is equal to -1. So for what we have in the case of the product of the square root of -9 and that of -4 is not going to be 6. Instead, we're going to have 6 times I squared, with I squared at -1. And we have the end result at -6 as opposed to +6. And just taking what we have, let's say, in reduction. Okay, so if I have with division, so I have, let's say, the square root of -9 all over the square root of -4. Okay, so square root of -9. Okay, so you can have, writing in terms of I, so I have 3i. Square root of -4 again is going to be 2i. And again, you're going to have the factors in I to cancel each other. And so for this ratio, okay, that will go to 3/2. Okay. Okay. Now with addition, subtraction, and division, the process is very intuitive. But with multiplication, again, since you're looking at multiplying like radical types, okay, again, with the terms, again, you want to go ahead and take out the letter I And again, I squared is equal to -1. And so, so again, once you're working with complex radicals, go ahead and express in terms of the variable I. Okay, and now, again, just going back to what we have with complex numbers. Okay, and let's say that okay, so if you're to write the results in terms of a plus bi, and we'll say we have as a first case. Okay, we'll say that we have let's say we have 3 plus the square root of -6, and we'll say that we have times the quantity of 2 minus, and say we'll have the square root of -24. Okay, and so we got 3 plus the square root of -6 times the quantity of 2 minus the square root of -24. Okay, and in terms of writing, okay, the complex radicals in terms of the variable I. So right now we're going to have 3 plus the square root of 6 times I. Okay, now for the square root of -24, I was going to mention, I'm going to go ahead and reduce this one. For the square root of -24, so the square root of 24i, and now the highest perfect square that will go into 24 is going to be 4. Okay, so I have 2 times the square root of 6i. So I got 3 plus the square root of 6i. And I have times the quantity of 2 minus 2 times, okay, the square root of 6 times I. Okay. And for what we have in the process, okay, so if I take the FOIL, okay, and so we have in the process, okay, so you have 3 times 2 is 6. Outside product, okay, so we have 3 times -2, so you have -6 times the square root of 6 times I. And then I'm going to have, for the inside product, so you have the square root of 6i multiplied by 2. So I have 2 times, okay, the square root of 6i. Now, in the case of what we have for the last product, so we had the, I'm going to do this one gradually. Okay, so you have -2, and you have times the square root of 6 times the square root of 6. So you have the square root of 36, I times I, again, that is going to be I squared. Okay, so we got 6. Now, for the terms in the middle, okay, so both of these are in the square root of 6 times I format. And looking at the coefficients in front, so you have a -6 of this plus 2 of that. And -6 plus 2 is -4. And then we have with the square root of 6i attached. Okay, we have the terms in the middle combined to -4 times the square root of 6i. Now for the last term, so I got -2. Square root of 36 becomes 6. And you're going to have I squared to come out to -1, and I'll put that on display shortly. Okay, so you have 6 minus 4 times the square root of 6i. -2 times 6 is -12. Once again, I squared is equal to negative 1 Okay, so negative 12 I squared, this will translate to plus 12. And so for what we have here, okay, so this will come out to 18 minus 4 times, okay, the square root of 6 times I. Okay, so that would be the resulting A plus BI form that we have in the product. Okay. Right. And just kind of just a quick once over. And if I have something like 3 plus 4i quantity squared, again, so for the square of a complex number that is already in standard form, it'll be that complex number times itself. And again, if I were to take the FOIL method, okay, so I have 3 times 3 is 9, 3 times 4i, so this will make 12i. Inside product, okay, we have it 12i. And for the last product, we have 4 times 4 is 16. So 16i squared. And again, we have 9. 12i plus 12i will make 24i. And again, I want to undo the presence of any raised powers in I. And again, I squared goes to negative 1. Okay, and so just bring down the 9 and the 24i. Okay, we have 16i squared translates to negative 16. And we have combining like terms together. 9 minus 16 is negative 7. And we have plus 24i. And this will be the resulting standard format for what we have in the results. All right, now in the crossover to what we have not only with multiplying, but also what's going to be carried out for what we have in division. And we're going to have what will be referred to as complex conjugates. And for what we have with complex conjugates, okay, you're going to have, say for a standard number, okay, we're going to have the conjugate of A plus BI is going to be, okay, it'll have the feel of about like difference of squares. And in fact, we're going to be heading in that direction. Okay, so the conjugate of A plus BI is going to be A minus BI. So you still have A and BI terms, where you have BI to be added in one term and then subtracted in the other. Okay, and just looking at what we have in the categories. Okay, so if you're looking at a number and determining the corresponding conjugate, let's say we have just kind of start out, okay, if you have, let's say 4 plus 3i. Okay, now for the conjugate, okay, so you have A plus BI represented by 4 plus 3i, and for the conjugate, Now you still are going to have 4 and 3i, but the 3i is going to be subtracted. So addition in one will be subtraction in the other. And if I have, let's say, like negative 3 minus 6i, again, the constant term at the front, that is the number that is not attached to I, okay, this is going to remain as it is. Okay, so you have negative 3, and for the conjugate of negative 6i, that's going to be a plus 6i. So we have a conjugate relation, and if I have, let's say, the number 17, okay, so I have the number 17, okay, so I is not attached, okay, so 17 is going to be reference to A, and the A elements in the original number is going to have the very same A elements in the conjugate. So 17 leads to 17. And if I have, let's say, negative 14i, the conjugate of that, okay, so you have the I term, and the conjugate is just going to be the opposite sign. We have, in this case, we have positive 14i. So going from numbers to their conjugates, okay, if I is not alongside, okay, the numbers will stay the same, like what we have with 4, negative 3, as well as 17. But if I is alongside, okay, we change the signs, like 3i, negative 6i, positive 6i, and then we have last negative and positive 14i. And now, regarding conjugates, okay, now for the product of conjugates, okay, we're going to have a real constant as the result. And let's say if we have, let me take just, for example, okay, say if I have, just kind of like with 4 plus 3i, 4 minus 3i. If I take the products, okay, FOIL out, so you have 4 times 4 is 16. And you have negative 12i for the outside product, positive 12i for the inside product. And the last product, now we have initially, you have negative 9 times I squared. And if you notice, we have negative 12i, and 12i will cancel each other out. And for negative 9 I squared, again, I squared comes out to negative 1. And negative 9 times negative 1 will be a positive 9. And so for the product of these conjugates, okay, this is going to come out to 25. Again, just sort of restating, if I have, let's say with conjugates, if I have, let's say, 7i times negative 7i, so I have 7 times negative 7 is negative 49. I times I becomes I squared. Once again, I squared is at negative 1. So the product of 7i and negative 7i will come out to positive 49. Okay. All right. Now, in the case of what we have with division regarding complex numbers, and okay, so taking conjugates, let's say of the denominator. Can be used to express complex fractions. Or I should say, can be used to convert let's say complex number fractions. To standard form. That is standard as an a plus bi. And we'll say that if we have, for instance, if I were to write, okay, in a plus bi form, and let's say if I have a complex number fraction, let's say if I have 2 over, let's say I have 2 over 3 plus I, okay, and again taking conjugates of the denominator, okay, so here for 2 over 3 plus I, now the denominator is 3 plus I, okay, so we have the conjugate of 3 plus I is going to be 3 minus I. So for what I have here, okay, in terms of taking conjugates, what I'm going to do here is I'm going to multiply this ratio by 1 in the form, okay, where we had the conjugate of the denominator divided by itself. So in this case, the conjugate of 3 plus I, the denominator is going to be 3 minus I. And we have with distribution, okay, so 2 over 3 minus I. Okay, so this will be 6 minus 2I. And we got 3 times 3 is 9. Okay, what's going to happen here? Okay, we got 9. Your outside and inside products are going to cancel out. So we have 6 minus 2I. And now we have 9 minus I squared. Again, we have I squared equal to negative 1. And so for what we're going to have here, so we got 6 minus 2I all over 10. Again, subtracting the negative, same as adding the positive. And looking at splitting up, so you have 6/10 minus 2/10 of I. And we can simplify what we have here, so we're going to have 3/5 minus 1/5 of I. Okay, so in this format, A will be at 3/5 and your BI will be negative 1/5 of I. And just with what we have in the groups, okay, so for what we have on page 80, okay, so you're just looking at taking complex radicals where we have on display. Okay, you just have the square roots of negatives. And kind of going back, okay, now we have for number 13. Okay, we're looking at the product of the square root of negative 10. And we have times the square root of negative 5. Okay, so you have complex radicals. Now, we have expressed as the square roots of negative values. And again, in terms of operating. Now, I can understand the temptation to take the square root of negative 10 times negative 5, but do not multiply the numbers yet. You want to go ahead and express in terms of I. Now, we have the square root of negative 10. So this would be the square root of 10 times I. And for the square root of negative 5, okay, so we have the square root of 5 times the I. And if I take the product, now I can take the product of the numbers inside the radicals as long as we do not have negatives. So I've taken care of the negative signs upon extracting the letter I for each. So I can multiply now. So I have the square root of 10 times 5, so this would be the square root of 50. And we have I squared. Now, square root of 10 cannot be reduced. Square root of 5 alone could not be reduced. However, the product between the square root of 10 and the square root of 5, that can be a reduced radical. And for the square root of 50, the highest perfect square divisible into 50 is going to be 25. And here we have square root of 25 is going to be 5. And we have times the square root of 2. And we have that I squared. Again, that is going to be negative 1. So we got 5 times the square root of 2 times negative 1. And we have for this end result, in reduced exact terms, we come out to negative 5 times the square root of 2. And for what we have in the case of the next item, okay, so we have with 18. Okay, so you have the square root of negative 80 over the square root of 5. Now for the square root of negative 80, okay, over the square root of positive 5, okay, so we have, we can write this extracting the I. So the square root of 80 times I over the square root of 5. And now 80, not a perfect square number, but it is the multiple of perfect squares greater than 1. And the highest perfect square that will go completely into 80 is going to be 16. If I branch out, so you have square root of 80 is going to be square root of 16 times the square root of 5. Again, we have I alongside it. And we have all over the square root of 5. And notice, okay, we have like terms between the numerator and denominator. So we can get the square roots of 5 out. And so this will become the square root of 16i, or the square root of 16 times I, and that is reducible to 4i. Right. So again, with operations between radicals, if there's at least one complex radical, go ahead and express that complex radical in terms of I. And for what we have in the case of 42, okay, so here we have the square of the difference between 10 and 3i, and we're looking at expressing in standard form. So we got the square of a number in standard form. So for the square of 10 minus 3i, so you have 10 minus 3i times itself, and taking the FOIL, So you have 10 times 10 is 100. Outside and inside products, okay, we have minus 30i and another minus 30i. For the outside product, we have a negative times a negative is a positive. But again, we have I squared in the attachment. So here we have 100, negative 30i minus 30i, we have a negative 60i. Now for 9 times I squared, we have 9 times negative 1. And bringing the other terms down, so you have 100 minus 60i minus 9. And we have 100 minus 9 becomes 91. And we have minus 60i. Okay, so that is going to be the A plus BI format. Okay, so A is at 91 and BI we have at minus 60i. Now, and looking at what we have, say for the next item, and in a way we do have conjugates in the mix, and the numbers are displayed in radical terms. Okay, so here we have the square root of 5 plus the square root of 7 times I. And we have times the quantity, so you have the square root of 5 minus the square root of 7 times I. Now the display could have originally been square root of 5 plus the square root of negative 7 times the quantity of square root of 5 minus the square root of negative 7. But here, okay, the author has already taken the complex radicals and expressed in terms of the letter I. So if we take the FOIL, and what I'm going to do here, I'm just going to multiply and just keep the radical notation at the present moment. So you have for the square root of 5 times the square root of 5. Okay, this will become the square root of 25. Outside product, okay, so you have positive times a negative is a negative. Square root of 5 times the square root of 7. We have the square root of 35. And again, we have the letter I is going to be attached. And then for the inside product, we have square root of 7 times the square root of 5 would be the square root of 35. And again, we have the letter I, again, will be attached. And then for the last product, we have square root of 7 times the negative of the square root of 7. So we have minus the square root of 49. And I times I becomes I squared. And if you notice, okay, we had the square root of 25. Okay, so that is going to be 5. And we have negative and positive, square root of 35i. Okay, so these terms are going to cancel each other. You have minus, now the square root of 49 is 7. And I squared is going to be at negative 1. So you have 5 minus 7 times negative 1. And so we're going to have 5 plus 7. And 5 plus 7 is going to be equal to 12. And if there were any other way to display, like if you had to give the I term exactly, well, to represent the void of an I term, you can say we have 12 plus 0i. Alright, and then we have crossing over, okay, into the threshold, okay, of working with, again, complex fractions. And this is where, again, the conjugates will be a good use. And we have for the case in number 51. Okay. So here we have 6 plus 2i. And we have all over 3 minus I. Okay. And just kind of signaling here. So I'm going to take the conjugate of the denominator. Okay, so the conjugate of 3 minus I is going to be 3 plus I. So in working with what we have, okay, so got the denominator at 3 minus I. And if I multiply by 1 in the form of the conjugate divided by itself, and we're going to have with distributing. So if I FOIL out the top terms, okay, so I got 6 times 3 is 18. And I got plus 6I plus another 6I. Last right, we have 2I squared. And we have in the denominator. Okay, so we're going to have 9 outside inside products. They're going to cancel each other. So plus 3I minus 3I, and we have minus I squared. So for right now, we've got 18 plus 12I. And for 2I squared, so we have 2 times negative 1. And for 9 minus I squared, so this would be 9 minus, so we have negative 1. Okay, so I have 18 plus 12I minus 2 all over 10. And as we get closer, so 18 minus 2 is 16. And so you have 16 plus 12I over 10. And if I itemize, getting into the official A plus BI form. Okay, so if I separate, have 16 over 10 plus 12 tenths of I, and both of these fractional coefficients can be reduced. So 16 tenths, this will be 8 fifths, and 12 tenths of I, this will go to 6 fifths of I. Okay, so this result will be what we have in explicit A plus BI form. Right. And now, for what we have in the case of the next item, okay, so we have nature of this pretty similar. Okay, you have 2 terms in the numerator, 2 terms in the denominator, and both the numerator and denominator, okay, are in standard form in their own right. And if I look at the reduction of the ratio and put into the standard format as well, okay, this will involve once again working with the conjugate of the denominator. Okay, so here the denominator we have 4 minus I, and so for what I have with the ratio, I'm going to multiply by 1 in the form of the conjugate over itself. So here I'm going to have 4 plus I over itself. And And just working with what we have now. So we got 5 times 4 is 20. I got plus 5i plus 4i. Last product, so we have I squared and here we have 16. Again, the outside and inside products are additive inverses. Alright, so for what we have in the follow through, so 20 plus 9i, and I squared we have at -1. And for the denominator, we have 16 minus. Again, I squared is going to be -1. So here we have 20 plus -1 is going to be 19. We have plus 9i. And for 16 minus -1, okay, that's going to translate to 16 plus 1, which will be 17. And then we have in separating this combined ratio, so we have 19 over 17 plus 9/17 of I. And both of the fractional coefficients are already in reduced form. So the a plus bi result is 19/17 plus 9/17 of I. All right. Now, in the case of what we have with single terms, and we have with, say, for number 55, and this one can technically be reduced in advance, but for 5 over 13i. Okay. Okay, so the denominator is 13i, and so the conjugate is going to be -13i. And so we'll take in the rewrite, so 5 over 13i. And if I multiply by the conjugates of the denominator, so we have -13i over -13i. And we have upon multiplying, so we have 5 times -13i, which is going to be a -65i. Now we got 13 times -13, that's a -169. I times I becomes I squared. Okay, so I squared again is -1. So right now we're going to have -65i over positive 169. Okay, and this ratio, okay, can be reduced because what's going to happen here is that, okay, greatest common factor of -65 and 169 again is going to be the number 13. So 13 to cancel out. So for the completely reduced form, so I have -5/13 of I, and if this were to be expressed in any other way, just to have A explicitly laid out. Now A is negligible, so the result here could also be written as 0 minus 5/13 of I. And then we have for the remaining one. Okay, now this one kind of has a roundabout way of getting to the result, especially once you have expressed in completely reduced form. And for what we have in the case of 56, okay, so we're looking at 6 over 7i. Again, so we have for the conjugate of the denominator, okay, that's going to be negative 7i. So for 6 over 7i. Okay, so I'm going to raise this using the conjugates. So multiplying by 1 in the form of negative 7i over itself. So we have 6 times negative 7i, so we have a negative 42i. And we got 7 times negative 7, so you have negative 49. And you have I squared, again, I squared goes to negative 1. Okay, so you have negative 42i over 49. And between negative 42 and 49, just like 13 earlier, okay, we already have 7 as the greatest common factor between the numerator and denominator. So we have 7s to go out. And so for what we have here, that should be 7 times 7. And so we have for the end result here, we have negative 6/7 of I. And again, just putting an explicit a plus bi form. Again, your a is negligible, so you just write 0 minus 6/7 of I. All right. So these are various forms of solving for complex numbers. And now for what we have in the crossover, okay, so we've looked at complex terms and reducing. And for what we have in the case of for equations that will have complex solutions, and it's like if you had a calculator and you tried to enter and solve for some of these equations, and the display is like no solution or no real answer. In a sense, that is correct if you're only looking at the results through the lens of the real number system. And you might have some that will have some real roots along with complex roots included. And let's say that for equations that have complex roots, if you have, let's say, in the case of solving for x, and let's say if we have an equation, say we have x squared plus 4 is equal to 0. Okay, now in this one, Okay, now we have x squared plus 4 is equal to 0. Okay, now a difference of squares you can factor, but in the case of the sum of squares, you cannot. And I'll just mention one might be inclined to say, well, would it not be x plus 2 times itself? But here's the deal. If I have x plus 2 quantity squared, now it's true that the output will have x squared and 4, but the thing is that the outside and the inside products will not cancel each other. So once you combine everything, you have not just x squared plus 4, but x squared plus 4x plus 4. So x squared plus 4, in terms of real number integer coefficients, this cannot be reduced. So in terms of any recourse, in terms of solving for x, I'm going to isolate the x squared term upon taking 4 away from both sides. Okay, so I'm going to have the x squared is equal to negative 4. Again, just a little reminder, if I have x squared set equal to p, then we have x equal to plus or minus the square root of p. Okay, so here we have p to be a negative, in this case, negative 4. And if we go from x squared to x, we have x equal to plus or minus the square root of negative 4. Again, so while the square root of 4 is 2, that of negative 4 comes out to 2i. So we're going to have, for x, we have exclusively two complex numbers with 2i and negative 2i. And another case too, where complex roots can exist. And this is going to have kind of a feel of the square root property of equality backdrop, okay, to the quadratic formula result layout. And if you have, let's say, something like the square of x plus 1, and say we have plus 36 is equal to 1. Okay, so I have for this equation, what I'm going to do here, I'm going to isolate the variable expression, which I have as the square of x plus 1. So the 36 I have alongside, I'm going to move by subtracting on both sides. So we have the square of x plus 1 is equal to negative 35. Okay, and with the square root property of equality, okay, so I have x to the second represented by x plus 1 raised to the second, and p is represented by negative 35. So if I drop the degree for x plus 1, going from second order to first order, I have x plus 1 is equal to what's going to be plus or minus, okay, the square root of negative 35 so you have with x plus 1, we have with plus or minus. Now the square root of negative 35, again, we have a couple of complex terms, which should be plus or minus, okay, the square root of 35 times I. And just like what I had done before when we were working with the real number system, I'm solving for x, not x plus 1. So what I'm going to do here is that I'm just going to lay this out in horizontal subtraction terms. And again, the reason for this is that I want the radical set to follow the constant. And so here we're going to have positive negative 1 to cancel out. And we have in compact terms we have x is equal to negative 1 plus or minus, okay, the square root of 35 times I. And just for what we have in separate terms, we have negative 1 plus the square root of 35 times I. Also we have negative 1 minus the square root of 35 times I. And except for the letter I involved, much of the methodology when we looked at the square root property of equality is very much reproduced. And now, and speaking of quadratic equations, if say we have an equation, and we'll say that we have here so we got 7x squared, and we'll say we have plus x plus 1 is equal to 0. Okay, now for this one, I cannot use the zero product property. In other words, if you tried out factoring by grouping, okay, so we have for the first and the last coefficients, we have 7 and 1. And if you multiply 7 and 1, okay, the product is 7, positive 7. And if you try to factor or determine factors of 7 that will add up to the middle coefficient, which would be 1, there's not going to be a combination because you got like 7 and 1, negative 7 and negative 1, and the combinations would add up to either 8 or negative 8. So we have is a bit of a recourse. So we have with the quadratic formula. Okay, so we have all the terms are positive. So we have from 7x squared, we have a is equal to 7, and from x, we have b is equal to 1, and since we have plus 1 at the end of the trinomial, we have that c is equal to 1. And in looking at what we have in x, okay, so you have negative b plus or minus the square root of b squared minus 4ac all over 2a So for negative b, we have negative 1, plus or minus, okay, the square root. And for b squared, okay, so you have 1 squared. And again, the minus 4ac parts, you must be careful with. Okay, so you have minus 4, a is at 7, c is at 1. We have all over 2a, which we have at 2 times 7. So you have negative 1 plus or minus. Okay, you have the square root. Now 1 squared is 1. Negative 4 times 7 is negative 28. Negative 28 times 1 is still negative 28. Then we have all over 14. Now we have negative 1 plus or minus. Now for the roots, okay, again, they're going to be complex. Now 1 minus 28 is going to be negative 27. And just stepping over to the side here. Okay, so we have the square root of negative 27. And that's going to be an I term. So you have the square root of 27 times I. Now 27, again, not a perfect square number, but it is the multiple of a perfect square that is greater than 1. And that perfect square is going to be at 9. So you have the square root of 9 times the square root of 3i. So the square root of negative 27 will go to 3 times the square root of 3i And now I could technically separate, but I'm going to leave the results here in compact form. So I'm going to have negative 1 plus and negative 1 minus 3 times the square root of 3i all over 14. And I could technically separate, have like negative 1/14 plus 3 times the square root of 3/14 of I. But I'm just going to leave this one in compact notation for now. Okay, right. And let's say that for what we have in the case of working with complex numbers, and let's say that just to kind of get things started. Say we try the following. Okay, say we have first of all, we'll say we have x squared plus 100 is equal to 0. And we'll say that we have next, we'll say that we have let's say we have the square of x minus 17 is equal to 47. And we'll say also that we have, and this is one where you don't have to worry about reduction so much. We'll say we have 2x squared minus 7x minus 1 is equal to 0. Okay, just looking at what we have for these three problems. Okay, so we have, first of all, we have, again, another sum of squares, okay, whereupon we have x squared plus 100, okay, is equal to 0. So we have, in this one, now, again, you could factor a difference of squares in the real number system, integers, okay, but for sum of squares, okay, you cannot. Okay, so for x squared plus 100 equal to 0, okay, so if I isolate, okay, the x squared term, okay, so once again I'm going to take 100 away from both sides. And so I'm going to have x squared equal to minus 100. And again, we have with the square root property of equality. So if I go from x squared to x, and with p represented by minus 100, okay, so I'm going to have that x is equal to plus or minus, okay, the square root of negative 100. And so I'm going to have additive inverse complex numbers with plus or minus 10i. So we have just separating the terms. Okay, so I have x is equal to negative 10i as well as 10i. Alright, so I have exclusively complex solutions for x. Alright, now for what I have, again, just for the second equation, and we have, again, the square of x minus 17 is equal to 47. And right away, okay, so I have the square of x minus 17 equal to 47. And if I go ahead and utilize, okay, the square root property of equality, so we have the squared expression x already by itself. So if I go from second to first order, okay, so I have x minus 17 is equal to plus or minus, okay, the square root of 47. Now 47 is a prime number, and the square root of 47 is already in simplest terms. And if I solve for x, okay, so I'm going to move 17 over. Okay, so I'm going to add 17 to both ends of the equation. And as I'm adding 17, so I'm going to take addition of 17 and put in front of the radical set. And so we're going to have in compact notation. Okay, so I have x equal to 17 plus or minus, okay, the square root of 47. And if I put in itemized terms, and so for what we're going to have in the mix, okay, notice we have real solutions throughout. So I have 17 plus the square root of 47. As well as 17 minus, okay, the square root of 47. So there was no I term since we had the square root of 47 to be other than the square root of minus 47. Okay, so these solutions were exclusively real irrational roots. And now, for what we have in the case of the next item, okay, and we might have real or complex roots. And here we have 2x squared minus 7x minus 1 is equal to 0. And now just taking what we have here. Again, if I were to try to factor 2x squared minus 7x minus 1, I would not be able to, at least not in terms of real integer coefficients. So here we'll have a at 2, b at negative 7, and since I have minus 1 at the end, I have that c is equal to negative 1. And for what we have in the case of x, so utilizing the quadratic formula, okay, so you have, again, negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a. And for negative b, so we have the opposite sign of negative 7. We have plus or minus the square root. And for b squared, okay, so I have the square of negative 7. And for minus 4ac, so we have minus 4 times 2 times negative 1. And we have all over 2a, okay, so we have 2 times 2. Okay, so you have the opposite sign of negative 7, so this would be 7 plus or minus. Okay, we have with the square root, negative 7 squared. Okay, so I have a negative times a negative is going to be a positive. And then we have negative 4 times 2 is negative 8. Negative 8 times negative 1 is going to be a positive 8. And 2 times 2 is 4. And so for what we're going to have here, we have 7 plus or minus what is going to be the square root of 57. And that is going to be all over 4. And I'll just leave this result in compact notation. Now for the square root of 57. Now 57, again, it has factors, but the highest perfect square divisible into it is just going to be 1. So the square root of 57 is already in simplest radical terms. Okay, so the first item had exclusively complex solutions, whereas the last two had exclusively real values. Okay, so there's like a momentary shift of gears. And let me give you, say just for this instance, okay, if I'm looking at where you're definitely going to have complex roots, and say if I have something like the square of x minus 10 is equal to negative 250. All right. So we have the square of x minus 10 equal to negative 250. Okay, so here, okay, we have the x expression, okay, by itself on the left-hand side, okay, and since the expression is squared, I can apply the square root property of equality. So going from x minus 10 to the second to just x minus 10, and have equal to plus or minus, okay, the square root of 250 Alright, now for the square root of 250, now 250 is not a perfect square number, but it is the kind of number that can be reduced. And if I were to factor out for the square root of, let's see, so let me back up here. So I got the square root of negative 250. And square root of negative 250, so this would be the square root of 250i. Now for the square root of 250, if I were to factor, now the highest perfect square that is divisible into 250, so that is going to be 25. So I got the square root of 25 times 10, and breaking it down, so I had the square root of 25 is 5. We have times, okay, the square root of 10. And just relaying back to what we have in this equation. So we have x minus 10 is going to be equal to plus or minus. Okay, we have 5 times, okay, the square root of 10i. And looking at isolating x, so I have x minus 10. So if I add 10, and on the other side, I'm just going to have the 10 out in front. Okay, so we have, for what we have here for x, so x equal to 10 plus or minus 5 times the square root of 10i. Okay. And just in the itemized notation, we have 10 minus 5 times the square root of 10 times I, and also 10 plus 5 times the square root of 10 times I. And we'll take just as remaining case. Okay, so if I have, let's say, 7x squared plus 3x plus 1 is equal to 0. Okay, so we have the 7 and 7x squared plus 3x plus 1. Okay, now this trinomial cannot be factored into integer coefficients within the real number system. And if we look at the use of the quadratic formula, okay, so for negative b, okay, so this will be minus 3. And we have plus or minus. Okay, we have the square root. Now for b squared, again we have 3 squared. We have minus 4 times a times c, so we have a at 7. and C at 1. We have all over 2A, so we have 2 times 7. Now for the activity we have inside the radical. Okay, so 3 squared, b squared is 3 squared, which is 9. Minus 4ac, we have negative 4 times 7, which is negative 28. Negative 28 times 1 is minus 28. We have all over 2 times 7, which is 14. And here we have negative 3 plus or minus, okay, the square root of negative 19 all over 14. So with the square root of negative 19, I know in ALEKS, okay, it wants you to draw out, okay, that letter I whenever there is a negative result from b squared minus 4ac. So we have negative 3 plus or minus the square root of 19 multiplied by I. You have all over 14, and some other ways you can express this. So this is the compact notation. And if I were to separate the addition from the subtraction, so we have negative 3 plus the square root of 19 times I all over 14, as well as negative 3 minus the square root of 19 times I all over 14. Okay. And those would be the results in this case. Now, so far with our equations involving the quadratics and all that, we've had so far our results to be either exclusively positive results or complex number results. And we're going to cross over next time into a category. Okay, we're going to have both types of solutions, a blend of real roots as well as complex roots for the ALEKS homeworks. Okay, so you have just the section R5 with the radical and the absolute value equations. That will be due Wednesday, the 27th at 11:59 p.m. And again, we have the class activity 1 set, okay, which will be due Saturday, and the ALEKS homework section R6, which we're kind of looking into. That set in ALEKS is due Monday, February the 1st, and the section R8 homework, okay, that'll be due Wednesday of next week. And I do have video simulations for these two particular sections in the weekly notes tab. And in terms of items, okay, to go ahead and be looking into, okay, we have on page 81 numbers 57, 58, 61, 68, 71, 92, and 94.